and welcome back to another video. And in this video, we're going to be taking a look at a paper 2 question from the IB Chemistry May 2018 Time Zone 1 batch. And now this is a continuation, or this is actually a part of question number 1. So it's part D of question number 1. And it starts off with saying urea can also be made by the direct combination of ammonia and carbon dioxide gases. Now, whatever is prior to this question is irrelevant because, as many of you may know, that even within questions, so example question one, within question one in a chemistry paper, there are so many subparts to that question. And I have picked out one specific subpart. So all the information we need to know is right over here. And I'm going to show you how to solve these questions. So urea can also be made by the direct combination of ammonia and carbon dioxide gases. They have given us the reaction over here. And they've also given us the enthalpy change. They haven't exactly specified what the enthalpy change is, but they've told us that it's less than 0, meaning it's exothermic. So they've told us first thing, state the equilibrium constant expression Kc. Now, this is one of the simplest things, simplest questions you can do, easy way to score 1 mark. What is the Kc? Kc for any reaction is equal to the concentration of the products times each other. Now, obviously, I don't know what the concentrations are, and that's why I have put it in this form. They're just asking for the expression. They're not asking for the actual value of Kc just yet. So they've just asked us for the expression. So the expression of Kc is equal to the concentration of the product multiplied by each other, divided by the concentrations of the reactants multiplied by each other. Now, why have I put this 2 here? In actuality, when you are writing the expression of Kc or calculating Kc, Kc is the concentration of the products or reactants, and you multiply them together. So what I've done over here, I've multiplied the products, the concentration of the products together. And when I write the expression, I should also remember that whatever the concentration of the product is, now in this case, I don't know what the concentration is, but whatever the concentration is, I have to take it to the power of the coefficient. And what I mean by that is, like I have done over here, NH3, it's in the equation, it is 2 NH3. So that's why I have squared it. If supposing over here it was 3 CO2, I would have cubed it. If supposing H2O was 7, I would have did it to the power of 7, right? But that's not the case over here. We just have 1, 1, and 1, and you can just kind of imagine there's a 1 over here. Really, anything to the power of 1, it really doesn't make a difference. So I just haven't written that. But you must know that you should put the concentration to the power of the coefficient of that element, whether it's in the products or the reactants, doesn't matter. Anyway, so this is the expression of Kc. So I'm just gonna put this whole thing over here. I'm gonna shrink this, which I think is a pretty cool thing. I'm learning to I'm learning to use this better or to my advantage these days, because it makes things so much easier than just rewriting everything and erasing and rewriting. I can just move things. It's like I have a special superpower. So that is Kc. I'm just going to make this. Yeah, there we go. So that's the expression of Kc. Now, predict with a reason the effect on the equilibrium constant Kc when the temperature is increased. Now, if you think this question is a bit tricky, it is actually not. You might look at this, even when I look at this, I get a bit confused, I get a bit hesitant. But remember, look at this, it's only for 1 mark, which tells you it's actually quite simple. And it is, and I'm going to show you how to predict something like this, and also what the reasoning behind it is. Now, Kc, as I said, it calculates the equilibrium constant using the concentrations of the reactants in the reaction. So in this whole reaction, it uses the concentration of the reactants to calculate the equilibrium constant. And of course, it also takes into account the ratios, like I mentioned earlier, whether you have to square it or cube it in certain cases or whatever the number is. So if we take or if we increase the temperature of this specific reaction here, where is the equilibrium going to shift to? Because remember, temperature does have an effect on equilibrium. I covered this in a previous video. Temperature does affect equilibrium, but the question is, which direction is the equilibrium going to shift in if we increase the temperature? And what we know from the question is that the forward reaction, this forward reaction over here, is exothermic because enthalpy change is less than zero, meaning that it is a negative enthalpy change, and negative enthalpy changes is equal to exothermic reactions, right? So if the forward reaction is exothermic, this would automatically mean that the reverse reaction is endothermic. But supposing if the forward, just imagine if the forward reaction was endothermic, then the reverse reaction would be exothermic and vice versa. But in this case, our forward reaction is exothermic as mentioned in the question. That means our reverse reaction is going to be endothermic. And if we increase the temperature, if we increase the temperature of this reaction, the reaction is going to do its best to maintain equilibrium, meaning it would do its best to maintain the temperature that it currently is, and it would try to counteract the effect of us increasing the temperature. And how would it do that? Well, it would do that by favoring the reactants or the reverse reaction, because remember, the reverse reaction is endothermic. So you can think of it like this. If you are sitting in a room and you're wearing a jacket and it's quite cold, but then suddenly I turn up the heater, right? I start making it warmer. You want to take your jacket off. Whereas once you've taken your jacket off, if I stop the heater and it becomes cold again, you put your jacket back on. Similarly like this, the reaction is trying to adjust, or it's trying to maintain the equilibrium by shifting to one side or favoring the production of either reactants or products. And in this case, because the forward reaction is exothermic and we are increasing the temperature, it's going to favor the reverse reaction because it wants to maintain the original temperature or the temperature it was at before we increase the temperature, right? So it's going to favor the reverse reaction. And if it favors the reverse reaction, that would mean that the concentration of the reactants will increase because it's favoring the reverse reaction, right? So that would mean that it's producing more reactants than products. And if it starts producing more reactants than the products, that would mean that our denominator, right? Because after all, the Kc is just a fraction, right? The Kc is a fraction. That would mean if we increase our denominator, that would mean that Kc keeps getting smaller. If the denominator keeps getting larger, Kc keeps getting smaller. And if you're a bit confused about why that happens, let me show you. Imagine you're dividing 4 by 2. This is equal to 2, right? So imagine this is 4 by 2. You can imagine Kc, you can imagine that that this is 4, the top value is 4, and the bottom value is 2. Gives us a Kc of 2. But now imagine that I increase our denominator. Imagine that our denominator becomes 4. Now we're getting a Kc value of 1, which is smaller. And if then I further go on and increase the denominator value to 8, this becomes 0.5, which keeps decreasing. And this increase over here happens because the concentration of the reactants keeps increasing, whereas the concentration of the products either decreases or remains the same, right? And in this case, we can see that we are favoring the reverse reaction, meaning the reactants is being favored, meaning the concentration of the reactants is going to increase. So the denominator is going to increase and Kc is going to decrease as a result. So what is the effect of increasing temperature on the equilibrium constant? Kc decreases. And they've also asked us to provide a reason. And the reason you can provide, you can say that reverse reaction is favored because forward reaction is exothermic. And this should be sufficient to get you your marks. And I'm so sorry for my terrible handwriting, but hopefully you understood what I said, or at least try to understand what I've written. Hopefully that concept is clear to you, and now you somewhat understand why Kc decreases and how does temperature affect the equilibrium constant. I've also spoken about this exact same thing in a previous video. So if my explanation today was not all right, please do go back and watch the other video, and maybe that will help you understand it better. Now let's move on to the next part. So this is the last question, or the last part of this question that I'm going to address. I've seen this question come up so many times as well, and it is very easy to solve. It's an easy 2 marks that you can get. It's basically rearranging an equation. It is actually more to do with math than chemistry. So they've told us, determine an approximate order of magnitude for Kc using section 1 and 2 of the data booklet. Assume delta G for the forward reaction is approximately 50 kilojoules at 298 Kelvin. Basically, what they're asking us in this question, they're asking us to calculate what Kc is. Well, how are we going to do that? We have no idea what the concentrations are, right? Because according to this, to calculate Kc, we need the concentrations of H2O, we need the concentration of urea, we need the concentration of carbon dioxide and NH3, and we have no idea what those are. So how do we calculate Kc? Well, there is actually another way to calculate Kc. And the hint should be from this using section 1 and 2. Now, if you flip to section 1 and 2 of your data booklet, you're going to see this formula to calculate delta G. Now, what on earth is this? What is this funky looking equation? What are these letters? What does it stand for? Let me tell you. Basically, if you want to calculate delta G is equal to negative gas constant. R is the gas constant, which is 8.31 joules, times the temperature in Kelvin, which is, they've given it to us, they've told us it's 298 Kelvin, times ln or natural log of Kc. Now we don't know what Kc is, so I'm going to leave it as Kc. And they've also told us what delta G is. They've told us that delta G is positive 50 kilojoules. Now, if math is your forte, unlike mine, I'm not very good at math. But if you are good at math, this should be cake for you. You should easily be able to solve this. You know, it is just rearranging the equation. But if you're someone like me and you're not very good at math, let me show you how to do this. The very first thing we need to do, right? The very first thing we need to do, or what I like to do, is that I don't like this joules over here. You know why? Because we have Gibbs, we've been given delta G in kilojoules, but gas constant is in joules. So I like to convert from joules into kilojoules, and I do that by dividing by 1,000, right? To keep the units the same. Now we have the right units. And now it'll be easy to solve this. And now, of course, you can use your calculator in paper 2. So the very first thing you need to do is just multiply these together. Just multiply these together, right? What do you get? Let me just do that 2 on my calculator. So when you multiply those together, you get negative 2.47638 times ln of Kc, right? Now, it's simple. It's simple. You just have to isolate this because this is your variable, right? You need to find out what this is. And in math, as we do, we isolate the variable. So what do? We divide both sides by negative 2.47638. So this cancels out. And we do the same over here. And then this leaves us with Kc. So, or at least ln of Kc. We know the ln of Kc. So ln of Kc is equal to this. And if you put this into your calculator, you get the answer as negative 20.19, right? Now we know that ln of kc is equal to this. Now what the hell do we do with this ln? How do you take this ln away, right? You can't just carry it over. How do you take a ln away? Well, the method to take away a ln from both sides, if you've done this in math, we do this in math AA, we do this quite frequently. I'm not sure about math AI, but I'm going to show it to you anyways. All you have to do is raise both sides, or you have to take e, which is this letter over here, you'll see in your calculator, and you have to do e to the power of whatever number you got on this side. In this case, it's negative 20.19. And you have to do the same on the other side. You have to do e to the power of ln of kc. Now, when you do e to the power of ln, this is basically just equal to 1. So e to the power of ln is just equal to 1. So that's why this cancels out, because it's just 1. So kc is equal to e to the power of negative 20.19, and kc is equal to, let's put that into the calculator, it is equal to 1.69 times 10 to the negative 9. That is the value of kc. And now I'm very sorry if you do not understand all this math terminology here, because I know, I am not very good at math either, but it just comes with practice. And I'm so sorry if I've done a terrible job at explaining the math behind it. I would highly recommend you to go and watch Revision Village or one of those videos to understand this a bit better, or just search it up online. And hopefully that'll help you. But I hope that I've managed to get the chemistry behind this to you, or how to tackle this question and the steps to do it. And this is our answer for this question, because they've asked us to calculate the Kc, and that is 1.69 times 10 to the negative 9. That is the value of our Kc. So that is it for this video. Hopefully I have helped you, and I've helped you learn something new or solved one of your doubts. I will see you in the next video with a brand new question. And before we go, remember, any question with this concept or any other concept, please feel free to let me know on my social media, by email, or put it down in the comments below if that's easier for you. And I'll be more than happy to help you. And thank you so much for everybody who's been supporting me or watching these videos, whether you're seeing this on Instagram or YouTube. I really appreciate it. And it gives me motivation to keep putting out new videos for you guys. So thank you so much. Goodbye, everyone. I'll see you in the next video with a new question.